Okay, so using the graph like we talked about last class. So I'll mention this, the work energy theorem, like I just mentioned a few pages ago, states that the work done by the sum of all forces acting on a particle equals the change in kinetic energy of the particle. Okay, so they like to write it like this, right? The work done equals the change in kinetic energy. This is sort of used mostly in cases where there's really not any potential energy. Although when there is, we can still say that the work done increases whatever the energies are that are given. Okay. So next class, we'll go over a little bit more about the potential energies, which is, I think, makes it kind of confusing, but just don't overthink it too much, right? You'll kind of be able to tell from the question how they want you to do it. Okay. But basically, the big idea that work changes energy is kind of the overarching thing. Okay. All right. So they could ask you something like this. Anytime you see a force versus displacement graph, okay, your brain should immediately start thinking energy. Okay. Because they like to show you, again, when you have the whole AP test or whatever, they'll be all different things. So when you see force versus displacement, that's your indicator that this is an energy problem. All right. So for this graph below, how much kinetic energy would be gained if an object was acted on by the forces shown below? Okay. So all you have to remember is that the area under the curve equals the change in whatever energy you're talking about. In this case, they say it's going to kinetic. Okay. So this is simply a matter of just 20 times 100 is 2,000 joules. And then 10 times 100 is what, 1,000. And then that's 500. So the change in kinetic energy is 2,500 joules. Okay. Right. So you're always thinking that energy is that area under the curve, or in some cases, it might be the derivative. The integral. Okay. All right. This is another question I pulled from some random place. An object moving at 10 meters per second in the positive direction experiences an applied force illustrated by the force versus distance graph. Okay. What is the net work on the object? And what is the final velocity of the object after experiencing the applied force? Okay. So when you see force versus distance and they want to know work, you're just looking for area. That's it. All right. Okay, so here, is this just going to be a box, basically, right? 2 times 2 is 4. 1/2 of that is 2. That's going to be a 2. That's going to be a negative 2, right? Because that's 2 times 2, 4, yeah. And then this is going to be 1, 2, 3 by 2, negative 6. Right, is that right? 3, yeah, negative 6. Okay, so my net work is going to be 4 minus 8. So it's going to be negative 4 joules of work. Okay. So this is an object that's going to be slowing down starting from I wonder if we need the mass of this. If starting from a velocity of 10 meters per second. Okay. All right. I feel like we need the mass for this, but let's see. All right. So if I'm thinking about my LOL, right, I'm going to have some initial kinetic energy. All right. And then I can see that some work has been removed from the system or taken out. So that's decreasing the energy, okay, which is going to leave me some final slower kinetic energy. Okay, so I'm going to have my initial minus the work equals the final. Okay, I like to write it like this. Not everybody writes it like that, but just to me that makes sense. Okay, instead of writing it work equals change in kinetic energy, I could do that too, but I don't like that. Okay. So let's see, 1/2 mv squared minus 4 joules equals 1/2 mv final squared. Okay, maybe not, I guess. All right, and notice I don't need to put a negative, right? That negative here is why I'm putting it on this side of the equation, right? Because it's coming out. So just be careful that you don't double negative yourself, okay? All right, so then I'm going to have 1/2 mv initial squared minus 1/2 mv's final square is 4 joules. Okay. And then I feel like I need the mass. Wouldn't I need the mass for this problem? Okay, let's just say mass is 2 kilograms. I'll just make a note of it in there. Okay. All right, so 1/2 times 2 times 10 squared. Okay. Oh, actually, I shouldn't have really reorganized it like that because that's kind of messing it up. Okay, minus 4 equals 1/2 2 VF squared. Okay, so that'll just be 1. So 100 minus 4 equals VF squared. So VF equals 96. Okay, and then you can see that's going to be a touch slower, right? Because it's under 100. So, oops, 96 divided by, nope, oh my God, what's wrong with me? Radical 96, 9.8 meters per second. Okay, right? So that's going to slow down. So just be careful, like, so you don't mess up the negatives. Just think, okay? Just think about it. I can see here that I have more area under the curve that's negative. So that means more energy is going to be removed from the system, which is going to make it slower, okay? And it does indeed come out a touch slower. Okay, I don't know if we missed something in this or whatever, but I'll just make up the mess. All right.